So now we're going to look at something called the common ion effect and how that works in solubility. So if you have a solution of calcium fluoride, it's dissolved in water, it's going to be producing a little bit of calcium and a little bit of fluoride. So kind of have to go backwards a little bit and remember your Le Chatelier's principle. So the solution already has fluoride in it. Right? If you were to add sodium fluoride to this solution, that would further add more fluorines. So what happens when you add product to a reaction? It shifts the reaction to the left. Okay? And so because of this, if you have a solution made up of one ion, and you add more of a solution that has the same ion, it actually decreases the solubility of the original compound. Okay, because of that common ion effect, you're adding more fluorine to a solution that already has fluoride. And so as a result, by adding sodium fluoride, you then decreased the solubility of the calcium fluoride. Okay? And you can actually show this in a calculation. So if we want to know what the molar solubility of calcium fluoride is in a solution that already has 0.1 molar sodium fluoride. Okay? So the equation is calcium fluoride makes calcium and 2 fluorides. Okay? And so now for our ice table then, same setup, but the initial values are going to be a little different. So the solution has sodium fluoride. So in terms of calcium, there's nothing. But it's 0.1 molar sodium fluoride, and sodium fluoride breaks apart into one sodium and 1 fluoride. So there's 0.1 molar fluorine already in the solution. Okay, the change for the calcium is going to be plus S, and the change for the fluorine is going to be plus 2S. And so at equilibrium, the calcium's concentration will be S, and the fluoride's concentration will be 0.100 plus 2S. Okay, and so the KSP will then be equal to calcium's concentration times the fluoride concentration squared. So we're going to be looking at S times 0.100 plus 2S squared. And then, like with all ice tables, anytime we have a variable that's being added or subtracted from a molarity, we just assume it's small enough that it doesn't matter. So ignore the 2S. So we end up with S times 0.100 squared. And so what's that? So we end up with KSP will be equal to 0.01 S. So we just need to solve for S. So S is going to be the KSP for calcium fluoride divided by 0.01. And a quick lookup shows that the KSP for calcium fluoride is 1.46 times 10 to the negative 10th. So the solubility will be 1.46 times 10 to the negative 10th divided by 0.01, or 1.46 times 10 to the negative 8th. Okay, so go ahead and give this one a shot at home. So, what is the most solubility of calcium fluoride in a solution containing 0.250 molar calcium nitrate? Okay, so the equation we're looking at is calcium fluoride breaks apart into calcium plus 2 fluorines, and the KSP for calcium fluoride is 1.46 times 10 to the negative 10th. All right. Nice table. We've got calcium. We've got fluoride. Okay, so initially, since calcium is already in the solution, we're at 0.25 molar, and the fluorine is at 0. After the change, this is going to go up by S. This is going to go up by 2S. And so the calcium will be 0.250 plus S, and the fluoride will be 2S. So KSP will be equal to calcium times the fluoride squared, 0.250 plus S times 2S squared. We assume S is small, and so we end up with KSP will be equal to, it's going to be 4S squared, equal to 0.250 times 4S squared. All right, so now solving for S, after we multiply everything through, we're going to get S squared will be equal to KSP over 1. 0.25 times 4 is 1. So square root, we get that S is going to be equal to the square root of 1.46 10 to the negative 10th, or 3 sig figs, 1.20 times 10 to the negative 5th. Okay, lastly, we're going to look at how pH affects solubility of these salts. And so it all depends on what the ions are, and whether they want or don't want hydroxides around, or hydroniums around. And so any kind of insoluble hydroxide then produces OH, and OH is a base. And so what you want when you have a lot of base around is, again, you want to exercise the Chatellier's principle. Well, how do you remove hydroxides from the reaction? Have hydronium around, have acid around. And so for insoluble hydroxides, a lower pH means there's a lot more hydroniums around. And as the salt dissociates in solution, those hydroniums are constantly reacting with the hydroxide and canceling them out. This effectively is removing products from the reaction. And Le Chatelier's principle states that if you remove product, the reaction shifts to the right. And so with these hydroxides, you want a whole lot of hydroniums around, meaning a really low pH, because that will increase the solubility. Because as the hydroxides are formed, they're being removed from the reaction by the acid, and so the solubility goes up. Okay. Same thing with things that make weak acids. So carbonate and bicarbonate are both very weak acids. And so so I'm just realizing there's a typo here. So it's for compounds that contain anions of weak bases. Okay. Same rule applies for the hydroxides. These will react with excess hydronium around and be removed from the reaction. And so since you're getting rid of product, once again, you shift the reaction to the right. Okay. So hydroxides and any reaction that produces weak bases, you're constantly shoving or removing product based on the hydronium reaction, shifting reaction to the right, and so solubility increases. Okay, so see if you can't figure out these problems here. So determine whether each compound is more soluble in acidic or neutral solution. All right, so you have to look at what they dissociate into to figure this out. So the barium fluoride dissociates into barium and fluorides. So if we go to page 751, that neat little chart there at the bottom, so it shows that fluoride is actually a weak base. So it's a weak base, meaning it wants hydroniums around, because if there's hydroniums, it's going to react with it and remove this from the reaction. So this guy is more soluble in acidic solutions. It needs hydroniums to remove fluorine from the reaction. Okay, silver iodide. This is going to dissociate into silver and iodide. So if we look at that chart, iodine is not on that chart, meaning iodine is not a weak base. So if anything, excess hydronium is just going to have more product around, which is going to force the reaction to the left. So you actually want this to be a neutral solution. Having any acid around doesn't help. Okay, calcium hydroxide. It's going to be calcium and 2 hydroxides. Hydroxide is on that list. It is a base. It's a strong base, but it's a base. And so remember, hydroxides want hydroniums around because the hydronium will react with this and remove it, shifting the reaction to the right, meaning more soluble. So this wants acidic solution. Okay, so with that in mind, would Fe iron carbonate or lead to bromide be more soluble in acidic solution, and why? So if we look at lead 2 carbonate, that's going to break apart into lead 2 and then carbonate. Lead 2 bromide is going to break apart into lead 2 bromides. So we look at that little chart there, and we see that carbonate, not bromide, is the base. And so since this is the base, the reaction benefits by having a bunch of hydroniums around because it removes it from the reaction, shifting the reaction to the right, which means it's more soluble. So the iron carbonate is more soluble in acidic solution due to the carbonate being a weak base.